Hi, welcome to lesson 15F, Derivatives of Logarithmic Functions. The goal of today is to differentiate logarithmic functions. So we're basically going to be dealing with the natural logarithm, or Logarithmus naturalis. That's going to be our function that we deal with. And I'm going to demonstrate use a little software application to show the derivative of the natural logarithm function, and then we can decide what kind of function results when we take the derivative of f of x. Okay, so we'll pause now and take a look at that. Okay, so here we see above in blue here is the graph of y equals ln x, and here is just a marker showing the x values, and this red dotted line is the tangent. The value of the tangent, or the gradient of the function at any point along the curve, is going to be shown down here in this graph down below, which is the gradient function. Okay, so I'm going to come up here and press play, and as this point moves along the function, we're going to see the gradient function appear here, and we're also going to see some values appear down in this table. Okay, so sit back and have a little look here. So by looking at this resulting function, this resulting gradient function, what does the function appear to be like? What familiar function do you know that this appears to be? We can take a look at the table of values here just to kind of verify. So when x equals 0.25, f prime of x is 4. When x is 0.5, f prime of x is 2. I'll skip down here to when x is 1, f prime of x is 1. When x is 2, f prime of x is 0.5. And when x is 4, f prime of x is 0.25. And then when x is 5, f prime of x is 0.2. Okay, so those are some of the key points. What do those points seem to indicate would be this resulting function, this gradient function of y equals ln x? So as you may have guessed, when we had x equals 0.25, f prime of x was 4. Actually, you didn't guess this, you were showing this. When x was 0.5, f prime of x was 2. When x is 1, f prime of x was 1. When x was 2, f prime of x was 0.5. When x was 4, f prime of x was 0.25. And when x was 5, f prime of x was 0.2. So all of this would indicate, I'm hoping you would see, that f prime of x was actually the reciprocal function 1 over x, which, as it turns out, is the case. So when f of x equals ln x, f prime of x equals 1 over x. Okay, so this is the derivative characteristic that you'll learn, or that you should know now. And the other thing is when f of x equals the ln of f of x, well, ln of, say, g of x, for example, then the derivative, f prime of x, equals 1 over g of x multiplied by g prime of x. So using the chain rule, we'll see that we do 1 over g of x, so the reciprocal like we did up here, and then we multiply by the derivative of that function. Okay, So let's now take a look at a couple examples, just for fun. So when y equals the natural logarithm of 5x, then dy by dx is 1 over 5x multiplied by 5. So derivative of ln x is 1 over, or sorry, ln of 5x is 1 over 5x, and then the derivative of 5x is 5. So that simplifies to 5 over 5x, which then simplifies to just 1 over x. Example 2, y equals ln x to the 4th power. Then dy by dx, well, we're going to do the chain rule here. So we're going to bring the 4 down in front, reduce the exponent by 1 to 3, and then take the derivative of the inside, which is 1 over x, and then we can bring it all together. So that would be 4 ln x all cubed all over x. Okay, moving along to example 3. We're going to have y equals ln of negative 4x to the power 4 all over x cubed minus 3 all to the power 5. Okay, so this is going to be a little bit more complicated. So we can use actually exponent laws to, or logarithm laws, which they come from exponent laws, to rearrange this and to make something a little bit easier to work with. So when you have a power in the logarithm, that power can come down in front. So we're not taking the derivative yet, we're just rearranging this. So the 5 comes down in front, so it's 5 multiplied by ln negative 4x to the power 4 all over x cubed minus 3. Okay, and then we can look inside here, and when we have division of a natural logarithm, we can then break that apart into a subtraction. Okay, so these are basic laws of logarithms. So that'd be negative 4x to the power 4 minus the ln, and this is sort of all multiplied by 5, the ln of x cubed minus 3. Okay, now that we have it in this form, now we can take the derivative of each part individually and make things a little bit easier. Okay, so the derivative, I'm going to put this over here, so the derivative dy by dx is going to be 5, there's that constant outside, and the derivative of the natural logarithm of negative 4x to the power 4, well, that's going to be 1 over negative 4x to the power 4, and then multiplied by the derivative of negative 4x to the power 4, which is negative 16x cubed. Okay, then we take and then we subtract, okay, because this is subtraction. And now we take the derivative of ln of x cubed minus 3, so it's going to be 1 over x cubed minus 3, multiplied by the derivative of x cubed minus 3, which is 3x squared, as I can squeeze that in, and square bracket. And then I'll just simplify this down a little bit. So I'm going to say this is going to be 5 multiplied by, and I'll bring this negative 16x cubed up on top here, I can simplify a little bit here, so maybe 16 divided by 4 is just 4. The negatives simplify down, so I'm just going to say this is going to be 4x cubed over x to the power 4. I'll simplify the powers of x in a second, and then I'll do negative and then 3x squared all over x cubed minus 3. Then now I'll simplify the powers of x. So 4 over x minus 3x squared all over x cubed minus 3. And then I'll get a common denominator and kind of bring these things together. So I'll get 5. So I'm going to multiply the top and bottom of this rational expression by x cubed minus 3, and I'll multiply top and bottom of this by x. So I'm going to have 4 x cubed minus 3 minus 3x squared times x all over x multiplied by x cubed minus 3. And then I'll just bring all this stuff together, so I'm going to multiply 4 times x cubed and 4 times negative 3, and then I'll end up getting 5, and then there'll be 4x cubed, and then here's a negative 3x cubed as I bring these two together, so that'll be x cubed minus 12 all over x multiplied by x cubed minus 3. And that will be the derivative of this complicated function here. Okay, and let's do one more just to finish off here. And for our final derivative of the day, example 4, by equals the ln of 4x squared multiplied by negative x cubed minus 4. And here we're going to be using the product rule. So dy by dx equals, so the derivative of the first multiplied by the second, so 1 over 4x squared multiplied by the derivative of this, which is 8x, multiplied by the second, which is negative x cubed minus 4, plus the first, ln of 4x squared, multiplied by the derivative of the second, which is negative 3x squared. And then we can kind of simplify a little bit. Probably won't be a whole lot we can do here, but we'll bring this together to give us 2 over x, and we got negative x cubed minus 4, and then bring this to the front, so we get negative 3x squared ln of 4x squared. And then what I'll do is I'll factor this negative out, and maybe I'll factor the negative out of both at the same time. So this negative comes out to the front, x cubed minus plus 4. Actually, I'll do that in the next step. Ln of 4x squared all over, sorry, I'm going to multiply this by x as well, so I get x cubed all over x, and then I'll bring the negative out, so it'll be negative 2x cubed plus 4 plus 3x cubed ln of 4x squared all over x. Okay, so that is the short version of derivatives of logarithmic functions. We'll have some time tomorrow to work on some examples, and then for you to work on your practice exercises. In the meantime, please look at example 11 on page 376, example 12 on page 377, and then on page 377 again, exercises 1, A, B, C, E, G, H, J, L, M, N, 2, A, B, D, E, G, H, I, 3, A, C, E, F, G, I, and 4 and 5. Okay, so thank you for watching, and we'll see you in class.